Yes, hello everybody and welcome to my brief lecture about the analysis of a transistor circuit with the signal flow grapher and Jupyter. This is actually part of a lecture I'm giving at the University of Applied Sciences and Arts, Northwestern Switzerland. But I think that what I'm doing right now is going to be quite interesting for a lot of people and also for the people who use our signal flow grapher tool, such that when this ends here I will upload it to my SwitchTube channel with all of those teaching videos. In case you do not know them yet, I will briefly copy the link into the chat. So on this channel here you will later find this video, and you already find there quite a few other videos we have here. Analyzing transistor circuits can be quite difficult, but together with the signal flow graph theory, of which you also find videos on the channel I just copied, and with the help of the signal flow grapher and symbolic Python, it can be quite quick and successful. So what I'm doing now is two things. The first one is I will go from the circuit to the graph together with you. So you will see how I can actually take a transistor circuit and directly draw a signal flow graph. And then second, I will do the simplification of this very complicated transfer function with symbolic Python. And there you will learn something on how to do circuit simplifications, actually, transfer function simplifications with the same method you would use by hand, but with a symbolic analysis tool. So let's just start. The circuit I want to talk to you about is this cascade gain stage here. I took it from the book Analog Integrated Circuit Design by Tony-chan Carusone and his colleagues. And in the book they give this circuit, and then they later say as an evaluation that the sum of the time constants is given by this here, and this formula is supposed to say something about the speed of the circuit. Now the question that you may have is, of course, how would I be able to analyze this? So the first thing you always need in the analysis of such transistor circuits is you need to know what the transistor is doing. And there are very many different ways in making a small signal equivalent circuit of a transistor, but the one I'm using here is a somewhat simple one. If this is my transistor and it has the gate and the source and the drain, what I will use here is the model that I will have a current source between the drain and the source here, and this is the drain current, and this is supposed to be the gate source voltage times the transconductance. At the same time we will also look at the source conductance, so there is a second current source in parallel to that. It is often drawn in the opposite direction, and this here is the voltage of the source and the bulk times GM, or GS is called. No, the other way around. I have to concentrate with the current directions. Source bulk it is times GS. So this here is the drain, and this here is the source. The controlling terminal is the gate. So the gate source voltage is taken here. There are also some passive components which go into the most simple of the transistor circuits, and one of them is the gate source capacitor. And one of them is the drain source conductance. And then you sometimes also use the drain gate capacitance, CGD. And what I'm now going to do with you is to draw a signal flow graph which contains all of these components in one graph and lets you calculate the transfer function from the input V in to the output V out of the circuit here with all those components in it. This is going to be a horrendously complicated transfer function which we will then simplify. Okay, I copy this. The first thing I always have to do when I want to draw a signal flow graph is actually go and give the nodes in the circuit numbers. And the numbers I propose here is here. This is the node number 1. Then this one will be the node number 2. And this one will be the node number 3. And I do not have more nodes in this circuit. So now I go over to the signal flow graph tool and I prepare a signal flow graph which has the same nodes here, and I will approximately use the same geometric configuration. So 1, 2, 3 should be rather vertical than horizontal. This comes from my thinking that if I do such a graph in the same way as I have the circuit, then I already know from the start that the graph will look relatively simple. So let me go over to the signal flow graph tool. And I have prepared an empty canvas for that. So what I now need is, as I said at the bottom, I need a node, and each node in my circuits has a current that belongs to it and the voltage that belongs to it. So here I would have the voltage of the current of the node 1 and the voltage of the node 1. So I try and label them. This is I1, and here I have V1. And then I have the current of the node 2 and the voltage of the node 2. So I do I2 and V2. And then I have the current of the node 3 and the voltage of the node 3. So I3 and V3. And always between the currents and the voltages I already draw in an impedance branch. But this I write as 1 over an admittance. And you see that I'm doing something strange here. So the paths I draw, they go left, right. So they change directions. But as those of you who already are familiar with the signal flow graphs know, it doesn't matter in which direction a branch goes on the paper, because these are just relationships between variables. The reason why I draw it like this here really is that I know if this goes like a zigzag here, then I will get fewer crossing branches on the paper, and the whole signal flow graph will be more pleasant to read in the end. I also have in my circuit some input voltage somewhere. This is the V in. And then I have some output voltage somewhere. This would be the V out. V out is just another name for the V3, so I simply make a branch of the weight 1, which is the equation V out is V3. So this is the signal flow graph prepared. And now what I will do is fill it up with the information of all of the components that I have in the circuit diagram. But for that I also need to prepare the Y1, Y2 and Y3, the so-called driving point admittances. And for that I briefly go over to the Jupyter notebook. So to give you an idea of what I will do, here I have already started filling filling it in with the title, Analysis of a Transistor Circuit. Yeah? And then below that, you see all the libraries I include. One of them is Hansby Tools. It's a library I maintain myself. If you don't have it, just do a pip install Hansby Tools in your Python installation and then you have it. And then I also have defined two functions I will use today. One of them I call nicety. With some of the Hansby Tools manipulation things, this will convert the transfer function into a nice form. And the other is called keeper. The keeper is something I like to do quite often. If I have a sum term of many expressions and I want to keep just the terms that contain one of the variables, then I can easily divide it by that variable, and then let that variable go to infinity and then multiply again with that variable, and the effect of doing this will then be that just the sum term with that variable is left standing. You will see that a little bit later. I will apply that keeper. Yeah. And here I will copy in the output of the signal flow graph tool, but after that I will need to define the driving point admittances. And the driving point admittances I already prepared. This is the Y1, which needs to have some value. Then I have the Y2 that needs to have some value, and the Y3. So these I will need to define outside the signal flow graph. This is Y2, and this is the Y3. I make this a bit nicer. So there you go. And they are not yet defined, so I need to define them. I hope this is not too boring for you. The intention of me showing you this is to show you how I really work when I analyze circuits. So this is you seeing me doing my job as an analog integrated circuit designer with the tools at hand. So this is approximately the speed I have when I really do the things. But now I'm all ready and set, and I can go back to the circuit diagram and actually have a look at all of those components in there. Now, those of you who have not yet looked into the driving point signal flow graph, please look at the videos at some stage, which are on my channel. I copy them again into the chat for those who came late. There you will see the whole theory about the driving point signal flow graphs. Now I will simply apply it. And the application goes like this. Yes, I already copied that. So the application goes like this. I pick one of the components. For example, this resistor here. And then I know that the passive component just gives me a branch between nodes, and it will go into the Y1 at that node. And I dislike resistors. I much prefer conductors, so I will use the GS to do that. So let me go over to the signal flow graph. And in the signal flow graph, this gives me one branch from the input, because it goes from the input to node 1. So this is the GS. And in the worksheet, the GS also goes into Y1. All right. Now probably I should also name it, otherwise Python will complain again. So this is now the first of the components. So one component done, next to go. This is a little bit hard to delete again. I would like to get rid of the yellow thingy here. Okay. Second component, which is already in the diagram, is the CL. So the CL is not hanging between nodes, it will just appear in the driving point admittance Y3. So this is where I put it. So in Y3 I will get S times the load capacitance. But I have neither defined S nor CL up to now. Another component done. If anybody watching this has a question, just please type it into the chat and I will check it and answer later. Yeah. But now for the next component, that was CL. So let's go to the components of the transistors. The most interesting, of course, is the GM here. Yeah. Here you have it. And the GM, these are sources that are in the channels of the transistors. So I could now draw it into here, the GM. This is one of them. And the other source of Q2 is hanging here. Now first let's go to the GM1. And this would be the GM2 source. So the GM1 is the source that makes a current from that voltage difference. And to take that into account in the signal flow graph, I just have to think about what effect will the voltage 1 have on the current. So voltage 1 increases, means the current increases, but the current flows out of the node 2. So what I actually have to draw into the signal flow graph tool is minus this is minus GM1. And the minus comes from the fact that I define currents into nodes as positive when they go into the nodes, and the drain current of that transistor actually goes out of the node. This is already everything I have to do for the GM1. That was the simple one. The more difficult one is the GM2, because the GM2 here is controlled by the voltage which is across this gate of the transistor. Let me tidy up that a bit. I think you can see it better if I remove the GM1 again. This you will remember that it was GS, so I can also remove it. So the GM2 here is controlled by the bias voltage, which is constant, and the source voltage. So if that voltage at V2 is going up here, then I have less current going into the node 2. So the voltage 2 controls the current of the node 2 as well. So from V2 to I2, I also have a negative GM, but this is the GM2. Here you see the graph. Yeah. But of course, this also influences the node 3, because this current is hanging between the nodes 2 and nodes 3. So here I have the GM2 also, but positive. So these signs of the currents are maybe the most disturbing things of the transistor analysis. They come from the fact that I have a direction here of this current which is down. But the node current of the node 3 is the current that goes into the node which is up. So I already have one sign change between the current through the transistor and the current into the node. In addition to that, the voltage at the node 2 going up means I have less current. So I have a negative sign from less current and another negative sign from the two arrows showing different directions. So in the end, the sign I get is a positive one. Yeah. So that's it. Here I have it. So this is already that source solved. I can remove that again, and then I take the next source. This is difficult to delete again. Okay, I can do it. Then I take the next source. This is the bulk effect current source. And the bulk current source again would be a current source which is between the source and drain of the transistor. Now I make it in a slightly different color here. So this would be one of them. And the arrow goes up. And this is the other of them. And the arrow also goes up. But now the controlling voltage is V source bulk. Bulk is somewhere else, VSB, for that one, and here it would be that one. So the lower transistor actually does not have a bulk effect, so the GS of the transistor 1 does not even come into play. But the GS of the transistor 2 does. And if you think all of the signs through, then you will find that the GS and the GM simply do exactly the same thing. So because of the different definitions, they have the same signs. They will anyway turn up in the same location in the graph, but they also have both plus or minus in the same place. So now I have also taken care of the GS. And so I go from component to component. I can tick this here, tick, or wait, I will with undo, remove here everything. So now it is clean again. So let's say tick, this is taken care of, this is taken care of, this is taken care of, this is taken care of. Next come some passive components. And where do they go? One of the GDS, the GDS1, is sitting here. So this is GDS1. Another GDS is sitting here. This is GDS2. Okay? And both of them are passive components. Now you see the GDS1 is just at one node, so it will... Oh, I showed you the wrong thing. Repeat again. I drew where you would see the GDS, so this is the GDS1 and the GDS2. They're sitting here. This is the GDS from that part of the circuit here. So they are just sitting across the channels of the transistor. So the GDS1 just goes from the node 2 to ground, and the only place where this occurs would be in the driving point admittance of the node 2. So this is GDS2. I also have not defined that yet. Let's do both of them. And I picked the wrong index. I'm talking about GDS1 of the lower transistor. That's the most dangerous thing always for me, is that when I have so many indices, I'm very prone to pick the wrong one. So now I have defined both of them. That was the GDS1 I showed you. Just goes from the node 2 to ground. The GDS2, however, is between the node 2 and the node 3. So it will occur in Y2 and Y3, but it will also cause branches between the nodes 2 and 3. So let's just first deal with the Y2 and the Y3, such that this is done. So here I would have plus GDS2, and here I would also have a GDS2. This is it already, but then they also occur in the signal flow graph between the node 2 and 3. So that means I would have from V2 to I3, I will also have a GDS2 in it, here. And from V3 to I2, the same. Here I have nothing yet, so this gives me a new branch, GDS2. Like so. And I do another tick on my list to do. So this is now also taken care of. I erase that from my drawing and say taken care of. So 2 capacitors missing. Let's first take the CGS. The gate source capacitors, they are hanging here. This is the CGS1, and they are hanging here. This is the CGS2. So you see that both of them are not between nodes, so they will not cause anything in the signal flow graph. They will just appear in the driving point admittances, and CGS1 in the admittance of the node 1 and CGS2 in the admittance of the node 2. So I put it there. So node 1 would have plus S times CGS1, and the node 2 would have plus S times CGS2. Plus, not times. This will otherwise give complicated and incorrect expressions. So I space the conductances and the capacitors a little bit. CGS1 is of course not defined, neither is CGS2, so let's define it. Okay. And then the last thing I have is the gate drain capacitors. I remove that. CGS is taken care of. So that we have. Now the last one is the CGD. Then we are finished. And the CGD, they are hanging here. This is CGD2 and this is CGD1. And the CGD2 is just hanging at the node number 3, so that's where I put it. The CGD, that's the CGD2 at node number 3, and the CGD1 is hanging between nodes 1 and 2, so it will occur in both driving point admittances, but also in the branches. Let's first do the admittances. So that's here. I said CGD2 is going to be in the node 3. And the CGD1 is going to be in both of the nodes 2 and 1. And here also. And of course, I need these symbols also. Gate drain capacitors. Good. Got it. But then, as I pointed out, this CGD1, that's this one, is also hanging between the nodes 1 and 2. So therefore, I will get forward paths in my driving point signal flow graph. So from the node number 2 to the node number 1, I will get an S times CGD1. And from the node number 1 to the node number 2, I will get the same. And this is it. Yeah, we have everything. So if I counted correctly, we will just make a final check, but I think I went through all of the components here. So let's do the final check. I took care of the CGD, the CGS, both of the current sources and the CGS of all of the transistors. So actually I am now finished with drawing the signal flow graph of that circuit. This signal flow graph now is a complete equation system describing my circuit. So I can now go and solve it. The signal flow grapher I'm using here can just do it by itself. So if I select the input and the output node I'm interested in and press generate Mason, then it calculates for me the Mason gain. So you people on the live stream don't see that window. It's not so important because the window which now popped up has also automatically copied everything such that I can paste it here. So this is the code that was generated by my tool. And if I now evaluate that code here, then I see that I get quite a complicated transfer function here for that simple circuit. So I don't have many transistors in that circuit, two actually of them, but already the transfer function looks quite complicated, and I have not even inserted my driving point admittances yet. If I substitute those also, so I call this the transfer function of the cascade stage, TC, that would be if I take T and substitute the driving point admittances, which I have just done with you, and then I get quite a complicated transfer function. If you are wild enough to expand that such that it multiplies out all of the expressions, then you will get something which, what shall I say, it's not going to help you a lot with the design of your circuit. Here it is. No, we don't even do that, I just delete it again. This is too complicated. And this is also why very often in the textbooks we have the authors provide simple solutions, and they show you how to actually do things. In this textbook here, they the one I took it from, they say there are shortcuts to derive a few of the time constants. Then if you have all of those time constants, you can more or less add them, and then you get the speed of the circuit more or less. This is the zero value time constant principle. I always forget the order of the name, yes. But it actually would work. However, they have 4 time constants here. And if we look at our transfer function, this doesn't have 4 time constants. You do not see that from the start. You would see that if you say, if you put this transfer function that you have here now into a polynomial form, and that's what my nice t I defined above is doing. So if I say, give me a nice version of the transfer function, polynomial in the numerator and polynomial in the denominator, I do not see much more yet, but what I see at once is that the highest power of the denominator transfer function is s to the power of 3. So that circuit here has 3 poles, not 4. So it will not have 4 time constants, but only 3. So what shall we make of that? And this is always a very good question. And always a very, very difficult to solve question. So the second part of my brief introduction into the tools is now, how do we go from this very complicated transfer function here to something we actually can deal with. Now, one thing that we can do is already the following. If you look at the circuit itself, you may get the idea that the drain gate capacitor may not be such a terrible thing. So where was it, the circuit? Yeah, the circuit was here. So the drain gate capacitor I have here between two of between the transistor here, the low transistor, this gate drain capacitor. It is hanging somewhere where I have a low impedance here, but this here is also a low impedance, so maybe I can just ignore it. And the first thing I would like to try is simply ignoring the gate drain capacitor here in my calculations. Now, to speed things a little bit up, I have prepared that and can copy that over from a different worksheet. In order for me to be able to copy it much more nicely here, I have to give it a different name. Otherwise the other things will not work. So I say that this is not TC, but I rename it as T62. And then I renice it again, and then let's see whether this still works. So this is T62. Because for my students, which are also listening right now, this was the exercise number 2 of the 6th teaching block I'm doing. So the idea what I have, which I have now, is to simply say what happens if the gate drain capacitance of number 1 of the transistor number 1 is 0. And then I see when I do that here the Y1 is suddenly occurring in all of the terms of the denominator, so I can actually factor it out. Yes. So let's do that. So I make a simplified version of my transfer function. This is tsimp. I factored it out, and then I make a simplified version of my transfer function here by also substituting my driving point admittance and just setting all of the gate drain capacitors to 0. Now we can of course always say how does he know that this even works? This is always the question in the textbooks. I now give you oh, you don't see that. Sorry. Could you please see what you are doing? Yes, I show it. From where on have you not seen it? Probably from here on. I guess this you already knew that I was doing it, yeah. But here, now I have substituted CGD1 into it. This I can delete again. And then I made the full transfer function with this simplification. So now I have made a simplification of this transfer function where you see that this driving point admittance of the node 1 is occurring in all of them. Yeah? And then I inserted all of the driving point admittances, and then I have the T62S, the simplified version of my transfer function, which could now be valid, or so I hope. And one of the big questions that people very often have when they look at these textbooks where they say, oh, you just neglect the CGD. Yeah? How do the guys know that they can do that? Well, I can tell you how they know. They know it from the same place where I know it from. I simply go and define a few component values. So typical component values, I think, that could be applicable here. Yeah? So this would be that. So I take all the GMs and the source conductance of 1 millisiemens. I have to define some of that. So just give me a second. Yeah, now that was the only one missing. So I have transconductances, source conductance, just typical values, and this is something that comes from experience, or if you have really calculated the circuit, you would actually know the real values. But typically the transconductance of 1 millisiemens is much larger than the drain source conductance. Here 10 microsiemens. I have load capacitors, other capacitors, so this would be typical values. And as soon as I have that, I can go and I can throw them into a body plot. So I arrange a body plot here. I cannot yet execute everything because I will make another function which is not ready yet, but here I would use the Hansby tools frequency amplitude stuff to make the data for a body plot, and then I have prepared for you the plotting also. I copy it over. So these are the plot commands which are used in Jupyter. Also here I cannot plot yet the next function I'm going to do, but this here I can already plot. And now I see a body diagram. The blue curve is the amplitude and the red curve is the phase. And here at this part of the curve you see a small difference between this, because the solid curves, this is the exact solution, and the dashed curves, this is my simplified solution without the gate drain capacitors. And you know what? It doesn't really make a difference, does it? So in this circuit here, ignoring all of the drain gate capacitors is actually quite okay, isn't it? Yeah, doesn't matter a lot. So this simplification was okay if the components have the orders of magnitude I have here tried above. So if this is the case, I can now make another attempt of simplifying this further. So the thing I told you before is that my simplified version here, it actually has the y1 always in the denominator. So if I type the t-simp again into it, here, simplified version, without inserting all of the things, then here you see the y1 which is always in the denominator. So if I'm interested in the speed of the circuit, let me just look at the denominator then, and the command to do that in symbolic Python is fraction. So nd gives me the numerator and the denominator. So if I just say this is nd is fraction so and so, and then ask for d, then I see the denominator of the transfer function. And then I will take this denominator and remove the y1 from it. This is actually the y1. So I get the simplified version of the denominator, which does not contain the y1 anymore. Of course, I must remember later to put y1 back. We will do that. But if you don't do that, then of course the result later will be wrong. But now we will have a much simpler solution, because now I can take this simplified denominator and evaluate it a little bit. Okay. So here I have the simplified denominator, put in all of the driving point admittances, remove the gate drain capacitors as we have already established that it's okay, and then converted it into a polynomial. And symbolic Python sometimes does difficult things. Every time you take the numerator and the denominator of some transfer function, it will not always do the same thing. If it is a negative transfer function, sometimes it will assign the negative sign to the numerator, sometimes to the denominator. Now it has picked the denominator, so it just removed the negative sign such that we see more. It's nicer. And now you see that the term in s square you cannot simplify. The term without s you cannot simplify, but that term here probably you can simplify a lot, because it contains large capacitors and small capacitors, and large conductances and small conductances. Of course you could now do it by hand somehow, but I will rather show you how to code it. So first I take this here and construct for you something which is DCT. I write it like this. Now what am I doing? I show you the result already. So what am I doing? I take the same as before and substitute everything and collect it. Like here, this is just the result what you saw above. And then with the next command, I say, please interpret that as a polynomial in S, as a Laplace polynomial. And the last one is, please give me all of the coefficients of that Laplace polynomial. Such that now I'm able to access the middle coefficient. So DTC1 is the middle one. So this is just the coefficient of S in that polynomial. And this puts me into the position where I can actually simplify that. Okay, so it seems to me that the largest conductance in this polynomial here is GM2, because the GDS2 and the GS2 are smaller, and I can try what happens if I say use this but only keep the terms with GM2. That's what the keeper function is for that I defined above. And maybe this works. I don't know yet. Have I now simplified too much? Is it still okay? And the only way to find out is to actually go and try it. So I make a new denominator here, and in this new denominator I take the whole polynomial, so the same I used before for the S square, the same I used before for the without S term, without S, but for S I just use the polynomial coefficient only with what I keep when I use the GM. But the y2 I must not forget. You remember down there the y1 I mean here. Later put y1 back, I wrote. This is now the time to do it because I removed it, so I multiply it back, but also substitute everything into it. So you see always the same substitutions, the same things I am doing. But this now gives me quite a nice denominator of my transfer function, doesn't it? It's very readable. And in this very readable transfer function here I can now define my idealized transfer function here with the numerator. That one I forgot to copy over. Where is it? Let me search for it. Here it is. Of course I also need to extract the numerator of that transfer function. So now I have the numerator of the transfer function and the denominator of that transfer function without the CGD. And this T62 I is now, I mean, it's outrageous, isn't it? Look at the simplicity of the transfer function that we have now got, yeah? And look at what we had before. I mean, it's no comparison, is it? I mean, this here is just useless. But what we have now, those of you who still remember everything you had from system theory or signal processing lectures or so, you already see that this is a low-pass filter function with one real pole and one complex pole, and you even could now guess the pole quality factor of that complex pole. And to make sure that what we did is okay, I can now simply also draw the signal flow graph of that, signal flow graph body diagram of that. Signal flow graph as before, and then I can check whether with those values here what I did was okay. It doesn't work yet. The phase looks very funny, but what I see now is that I have again lost the sign. This is the dangerous thing here when you do something with numerators and denominators from different functions. Then it can be that you just get the minus of the transfer function wrong. But this you very quickly see in the phase of everything. So once I have corrected that one, I get the amplitude and the phase. And the changes we have made seem to have changed the DC gain a little bit. If you don't like that, you can correct it back. And it seems to have made our circuit a tiny little bit faster. So the phase loss comes at a little bit higher frequencies, but other than that I would say that those two transfer functions look almost the same. So that was 50 minutes where I went from zero, empty sheet of paper, just a circuit on it, with all the explanations for students, to a simplified transfer function for that cascade gain stage, which has an advantage if you compare it to the original, that this one I think is much more correct, because the circuit here really doesn't have 4 time constants. It doesn't, because you have 3 nodes, 1, 2, 3, and with 3 nodes you can only have 3 poles. So that's it, all I wanted to show you. The point of that was really also to give people who are new to using the signal flow grapher an idea of what you can use it for. So you know, saw the signal flow grapher, a little bit how I use it. You saw symbolic Python, how I actually use it in my daily work, and you got a nice explanation of one circuit. I hope you enjoyed it and learned a lot, and if you want to know more about that, don't hesitate to get into contact with me. Also, if you would like to get the JSON file to load into the signal flow grapher, or get the Jupyter notebook that I just made here in this online lecture, then please write me an email to hanspeterschmid@fhnw.ch and I will send it to you. It's a little bit hard to provide a file download link with this video, because I'm sure this video will suddenly appear in different channels. So the safest thing is write to me and I will send. Thanks for watching, and I hope you visit my channel again at some stage.